That's a 70 billion parameter language model. It is running on the laptop I'm filming this on. Airplane mode is on. Nothing is leaving this machine. No API, no server farm, no subscription. Just weights on my SSD and a chip doing matrix math. Here's why that shouldn't work. The weights of a GPT-3 class model, stored the normal way, are 326 gigabytes. That's not disk. That's how much memory you need just to hold the thing. My laptop has 36. So, over the next 20 minutes, I want to walk you through how the open source world pulled this off. The 4 or 5 papers that actually made it possible, with the real numbers from those papers. Because the story is better than they compressed it. At one point, deleting the wrong 0.1% of a model lobotomizes it. At another, someone quantizes the compression metadata of the compression metadata. It's a good ride. Welcome to Nerdy Dives, where we take one deep technical topic and actually understand it, end to end. Today, how a 140 gigabyte language model ends up running for free on the machine in front of you. Okay, first, let's actually size the problem, because the arithmetic is stupidly simple and almost nobody does it out loud. A language model is, for our purposes, a giant pile of numbers called weights. Train it in 16-bit floating point, and every weight costs 2 bytes. 7 billion parameters times 2 bytes, 14 gigabytes. 70 billion, 140. So, can I run this model, is question 1, and it's pure arithmetic. Does the thing fit in memory? But here's the part that changes how you think about everything downstream. Question 2 isn't, is my GPU fast enough? It's, is my memory bus fast enough? Every time a model generates one token, it has to read essentially every weight in the network once. Read 14 gigabytes, do a little math on it, emit one word piece. Read 14 gigabytes, emit the next one. The MIT team behind a paper called AWQ measured this properly on an RTX 4090. That card can do 165 teraflops of compute, but it can only pull 1 terabyte per second from memory. And token generation does roughly 1 floating point operation per byte it reads. 1. To keep that card's math units fed, you'd need 165. So during generation, your GPU is basically a Ferrari in a parking garage. It spends almost all its time waiting for weights to arrive, which flips the whole optimization problem on its head. If inference speed is bandwidth divided by model size, then making the model smaller doesn't just make it fit. It makes it faster, nearly linearly. Shrink weights 4x, get roughly 4x the tokens per second on the same silicon. Same paper. Quantizing weights to 4 bits lifts that arithmetic intensity number from about 1 to about 4. Still memory bound, but 4 times less starved. And one more measurement from that paper that seals the strategy. They broke down memory traffic and found weight reads dominate activation reads by orders of magnitude. So you don't need to compress everything. Compress the weights, leave the activations alone, and you've attacked 90-something% of the problem. That's the entire game plan for this video. Shrink bytes per weight without breaking the model. The naive version of that idea fails in a really interesting way. Which brings us to the outliers. Quantization, mechanically, is easy. You've got weights stored as 16-bit floats, huge dynamic range, fine granularity. You map them onto integers. 8-bit gives you 256 possible values, and you keep one scaling factor per block to convert back. Round every weight to its nearest notch. Half the memory, basically for free. And for small models, this just works. Then, in 2022, Tim Detmers and collaborators tried to scale it and found something genuinely weird. One of my favorite empirical results in this whole literature. Naive 8-bit quantization tracks full precision perfectly, up to about 2.7 billion parameters. Then at 6.7 billion, it falls off a cliff. Not degrades, cliff. And the reason is that transformers, once they get big enough, undergo what the paper literally calls a phase shift. Big transformers develop outlier features, a handful of hidden dimensions that carry values up to 20 times larger than everything around them. And they're absurdly systematic. At the 6.7b scale, the paper counts about 150,000 individual outlier values per sequence, but they all live in just 6 feature dimensions. 6 columns, out of thousands, across the entire network. Below 6.7b, they show up sporadically in maybe a quarter of layers. At 6.7b, phase shift, every layer, 3/4 of all token positions. Here's the payoff of the wrong 0.1% teaser from the intro. The authors ran the ablation you'd want. Just zero those dimensions out. They're only 0.1% of the features, who cares? And see what happens. Delete the 6 outlier columns. Attention falls apart. Top 1 probability mass drops over 20%, and perplexity degrades by 600 to 1,000%. Delete the same number of random columns. Nothing. 0.1% effect. So this tiny set of dimensions is somehow load-bearing for the entire network's attention mechanism. The model has spontaneously organized itself around a few very loud channels. And that's why naive quantization dies at scale. Your 8-bit grid has 1 scale factor per block. It has to stretch to cover those plus or minus 60 monsters, which means the ordinary plus or minus 1 weights get squeezed into 2 or 3 usable notches. You've spent your precision on 6 columns and starved the other 99.9%. Detmer's fix, LLM.int8, is almost anticlimactically clean. Pull the outlier dimensions out, compute just those in 16-bit, do everything else in 8-bit, add the results. More than 99.9% of the multiplications stay in int8. The FP16 sliver costs about 0.1% extra memory, and quantization becomes lossless up to 175 billion parameters. Memory footprint, roughly halved. 1.96 times smaller for Bloom 176B, which was enough to put a 175B model on a single server of consumer GPUs for the first time. Half is nice, but half of 140 gigs is still 70. To get this stuff onto laptops, 8 bits had to become 4. And at 4 bits, rounding to nearest isn't just lossy, it's catastrophic. 4 bits per weight. 16 values. You're taking a number that used to have 16 bits of nuance and forcing it to be one of 16 options. 2 papers cracked this from opposite directions, and both are worth knowing because every model you download today was squeezed by a descendant of one of them. First, GPTQ, out of IST Austria and ETH Zurich. Their framing. Don't round each weight in isolation. Weights work as a team. When you round one weight and introduce error, you can adjust the weights you haven't rounded yet to compensate. GPTQ does this with approximate second-order information. Curvature, essentially. How sensitive is the layer's output to each weight? Solving layer by layer in one shot, no retraining. And it's fast. A 175 billion parameter model quantized in about 4 GPU hours on a single A100. The paper notes that doing this with retraining-based methods would extrapolate to weeks. Now the results table, because this is the best chart in the whole literature. Full precision OPT 175B scores a perplexity of 8.34. Naive round to nearest at 4 bits, 10.54, which sounds close until you realize that's worse than a full precision model 1/10 the size. GPTQ at 4 bits, 8.37, 0.03 of a point. You cut the model's memory by 75% and paid 0.03 of perplexity. And at 3 bits it gets comical. Round to nearest collapses to a perplexity of 7,300. The model is emitting noise. GPTQ, same 3 bits, 8.68. Still a functioning 175B model. Oh, and a fun trend from the same tables. Bigger models are generally easier to quantize, not harder. The scaling gods were merciful exactly once, and it was here. Second paper, AWQ, from Song Han's lab at MIT, the activation-aware idea. Their observation rhymes beautifully with the outlier story from Act 2. Not all weight channels are equally important, and here's the kicker. You can't find the important ones by looking at the weights. You find them by looking at the activations flowing through them. A modest weight multiplying a consistently huge input is a load-bearing weight. Their experiment, OPT 6.7b at 3 bits. Quantize everything. Perplexity 43.2, badly damaged. Keep just 1% of channels, chosen by activation magnitude, in full precision. 13.0. 1% of the weights was carrying that much of the model. But mixed precision is annoying for hardware. You want one uniform kernel. So AWQ does something elegant. Scale the salient channels up before quantizing, and scale the activations down by the same factor. Mathematically, it cancels. The layer computes the same function. But the important weights now occupy more of the quantization grid, so they survive rounding. Same 13.0 perplexity, 0 mixed precision, and no backprop or reconstruction anywhere, so it doesn't overfit its calibration data, which is why AWQ quants generalize well to chat-tuned and even multimodal models. And remember Act 1. Smaller weights means faster tokens, because memory bandwidth is the wall. AWQ's own runtime clocked 3.2 to 3.3 times real speedup over FP16, and they demoed llama.cpp on a mobile-class GPU. Their showcase box is a Jetson with 8 gigs of memory pulling 15 watts. So by 2023, the math existed. What turned the math into a thing your non-ML friend can brew install? A Bulgarian systems programmer and a leaked file. March 2023. Meta's Llama weights leak onto the internet, and within days, Georgy Gerganov releases llama.cpp, a from-scratch inference engine in plain C and C++. No Python, no CUDA required, no framework. It ran a real LLM on a CPU, on a MacBook. Within weeks, the community had it running on phones and Raspberry Pis. Every 4-bit trick we just covered suddenly had a delivery vehicle that compiled anywhere. Out of that project came GGUF, the file format that's now basically the MP3 of local AI. One file containing everything: weights, tokenizer, metadata, chat template. Download it, point any llama.cpp-based runtime at it. Done. Inside, weights live in blocks with per-block scales, direct descendants of the ideas from Acts 2 and 3, with llama.cpp's own k-quant mixtures deciding, per layer, which parts of the network get more bits. Embeddings are precision-sensitive. Parts of the feed-forward layers can go very low. There's even an importance matrix calibration step. Same philosophy as AWQ. Measure what matters. Protect it. 2 systems details worth appreciating. 1. Llama.cpp memory maps the model file, so the OS pages weights straight off your SSD on demand. That's why multi-gigabyte models open near instantly. 2. It can split a model between GPU and CPU, offloading however many layers fit in VRAM. That flexibility, partial offload, is what makes weird consumer hardware combos viable. And here's the thing most users never realize. Llama, LM Studio, Jan, the friendly apps, are all shells around this same engine. GGUF is the common language. When you type Llama run, you are, several layers down, running Gerganov's kernels over block quantized weights whose error bounds were established in the papers we just walked through. Quantization shrinks the bytes per weight. 2 other levers shrink the work itself. Lever 1. Distillation. Hinton and colleagues, 2015. Train a small student model to imitate a big teacher, And crucially, train it on the teacher's full output distribution, not just the right answer. The teacher saying 62% cat, 21% dog carries way more information per example than a label saying cat. That's why a 2410 survey of small models notes distillation from a strong teacher can beat pre-training a model of the same size on the same data. And it's the recipe behind things like the DeepSeek R1 distills, frontier model reasoning behavior transplanted into 7 and 14B bodies that quantize down to a few gigabytes. Lever 2. Sparsity, mixture of experts. Instead of one dense network, the model holds a large population of expert subnetworks, and a router picks a few per token. OpenAI's own Open Weights release, GPTOSS, is the clean example, straight from their model card. The 120B version has 117 billion parameters, but activates only 5.1 billion per token. The 20B version, 21 total, 3.6 active. You still pay memory to store all the experts, but per token compute and bandwidth pressure look like a model a fifth the size. Stack MOE with 4-bit quantization, and that's how a 20B class reasoning model ends up running comfortably in 16 gigabytes. Last chapter, because local isn't just inference. Fine-tuning a 65B model the standard way needs more than 780 gigabytes of GPU memory. Weights, gradients, optimizer states, the works. QLoRA got that under 48. One professional GPU, matching full 16-bit fine-tuning quality. 3 tricks, and they're all delightful. 1. NF4, a 4-bit number format whose 16 values are placed at the quantiles of a normal distribution, because trained weights are roughly normal. Information theoretically optimal notch placement. 2. My favorite. Double quantization. The per-block share constants were eating half a bit per parameter, so they quantized the quantization constants. That alone claws back about 3 gigabytes on a 65B model. 3. Paged optimizers, letting optimizer state spill to CPU RAM during memory spikes instead of crashing. Freeze the 4-bit base, train tiny low-rank adapters on top, and the result? Guanaco hit 99.3% of ChatGPT's score on the Vicuña benchmark after 24 hours on one GPU. The 7B variant is a 6 gigabyte file. The paper fine-tuned over 1,000 models to prove the recipe. That's the moment local stopped meaning run someone else's model and started meaning shape your own. So, the answer to the cold open. A 140 gig brain fits on a laptop because a phase shift discovery made 8-bit lossless. Second-order rounding and activation-aware scaling made 4-bit nearly free, 3/100ths of perplexity. A C++ hacker made it all a single, portable file. Sparsity made big models compute like small ones, and QLoRA made them yours for the price of one GPU day. None of this was one breakthrough. It's 5 or 6 groups, each attacking a different term in one equation. Tokens per second equals bandwidth over bytes. And the deeper thing, every paper in this video is public. Every method is in open code you can read tonight. The bibliography's pinned, with page numbers for every claim I put on screen. If this made the compression stack click, subscribe for more deep dives, and drop a comment with the topic you want unpacked next.